Right, so now we have this expression of K, reaction rate constant, to be a function of the of Boltzmann constant, temperature over the Planck constant, and function of the exponents minus the enthalpy of activation of RT times the exponents of delta entropy of activation over R. Okay. Now in the graph, the potential energy graph, potential energy, okay, where this is A, B plus C, and this is A plus BC. Okay, so this now, the free energy difference will be delta G double dagger, right? And this is the activated molecule. Now we can then group or rearrange this K into this term. Okay. Now for bimolecular reaction in the gas phase, right? So the energy activation is equal to the enthalpy of activation plus 2RT. So if we rearrange this, enthalpy of activations will be equal to energy activation minus 2RT. Right? So then we can substitute this term here, which will give us EA to RT over RT, right? This will be e to the power of 2 and e minus EART. All right. Now this looks very similar now to the Arrhenius law. In Arrhenius, we simply just write K equals to A times e to the power of minus EA over RT. Right? Now, with the transition state theory, it gives a physical meaning of what A is. Okay? So all of this term is A, Arrhenius pre-exponential factor. Okay. Okay, so this relation holds for bimolecular in the gas phase. So with the transition state theory, we are able to give a physical meaning of what A represents in the Arrhenius equation, right? Based on the idea that there is an equilibrium between the reactant and the transition state, right? So if we look at the initial step in the derivation, reaction rate constant is equal to the kBT over h, which is the frequency, right? This is the frequency of the transistor activated complex molecule decomposing into a product, times the equilibrium constant for the formation of the activated complex. Okay, so if you look at the expression of equilibrium constant, so it is equal to the concentration of the activated complex over the reactants. So if you want to make the reaction rate constant large, we have to make the equilibrium favoring to the concentration of the activated complex, right? And the activated complex equilibrium constant equals to is a function of the Gibbs free energy of activation, delta G double dagger here, which is in the plot of potential energy profile. That's the gap here, whereas this term, the difference in the free energy between the product and the reactant, this is the Gibbs free energy of the reaction, delta GR. Okay, so please be aware of this distinction. The free energy difference between the activated complex and the reactants is called delta G double dagger, which is here. All right. So, and the free energy, Gibbs free energy difference between the product and the reactants is called delta G, delta GR. Right. Okay. So what is this? What is this gives us? So now we know that A is as a function of temperature, right? A, or the Arrhenius pre-exponential factor, is a function of temperature coming from this term, and it's a function of its molecularity also. So there's this formula under a constant volume. The energy activation is equal to the enthalpy activation plus MRT. Our gas constant T temperature, M is the molecularity. For a unimolecular reaction, M is equals to 1. For bimolecular reactions, as what we have in this example, M is equal to 2. All right. So A is a function of temperature and a function of entropy activation. Now this means so what can we learn from the derivation using the transition state theory is that to increase the reaction rate constant, we have to increase temperature, and we have to increase the entropy of activation, right? If the entropy of activation increases, the reaction rate constant increases, right? But the opposite is true for the activation energy. If the activation energy decreases, the reaction rate constant increases at that temperature, right? So the energy of activation is related to the energy barrier that needs to be overcome in bringing the reactant to the activation activated state, right? Whereas the entropy of activation is related to the orientation, the stable orientation of the activated state, right? So when we decrease the activation energy, right, so the K will become larger.